All right, guys, today we are going to actually apply the 5 equations of kinematics, and we are going to solve some problems. So we're going to start off with the constant acceleration problems. So we're going to draw a diagram, then we're going to write out the values we know. We're going to identify what we need to solve for, define positive and negative directions, choose an equation that involves what you know and what you're solving for, then we're going to solve. Step 6, 7, and 8, it doesn't have on here, but step 6 is to substitute our values. So if we have a negative, depending on our directions. 7 is to solve. And 8 is to give a statement, or a therefore statement with significant figures and directions that answers the problem. So let's look at the first problem that we're given. It says a motorcycle travels west, increasing its speed from 6.5 meters per second to 9.2 meters per second through a distance of 48 meters. And it wants to know what is the motorcycle's acceleration. So the first thing I need to do is draw a diagram. And I have this big white space at the top of my paper. You have all this room down here. So the first thing I'm going to do is draw a diagram. And I'm going to draw a motorcycle. I am not the most gifted illustrator in the world. Here's my motorcycle. Looks more like a scooter. I've got a person sitting on it. Oh dear, he's going to have to reach a really far way to get to the handlebars. He's got really long arms. Okay. And it's traveling west. So we know that this direction is west. It's increasing its speed from 6.5 meters per second to 9.2 meters per second. So we know its initial velocity is 6.5 meters per second. So that's how fast he's going right here. And we know he's moving, so I'm going to give him some moving lines. His final velocity, it says, is 9.2 meters per second. So by the time he gets down here, here's his handlebars. He's going to sit right here. He's got some handlebars and a head. So by the time he gets down here, his final velocity is 9.2 meters per second. We know the total distance is 48 meters. And this is a vector, and it gives us a direction. He's traveling west. And it wants to know what the motorcycle's acceleration is. Okay, so we've done step 1. Step 1 was to draw a diagram. Step 2 is to write out the values you know and the values you don't know. So we know I'm going to write out the 5 kinematic variables. So I have initial velocity, final velocity, displacement, acceleration, and change in time. Those are my 5 kinematic variables. The problem tells us that our initial speed is 6.5 meters per second. And he's traveling west. It tells us our final velocity is 9.2 meters per second. We're still going west. It tells us our displacement is 48 meters west. And the problem is asking for acceleration. So this kinematic variable, change in time, isn't applicable here. So we need to look at our kinematic equations, and we need to find one that has initial velocity, final velocity, change in displacement, and acceleration. And I'm just going to go through the list. So I'm going to start at 1. So does one have initial velocity? My answer is yes. Does it have final velocity? Yes. Acceleration? Yes. Change in time? That's not going to work. We don't have change in time and we're not looking for it. So let's go to the next one. Initial velocity, final velocity, displacement, acceleration is missing, so that's not going to work. All right. I'm just going to go ahead and start with change in time to make this easier. And 3 and 4 both have change in time in them, so that's not going to work because we don't know that either. All right, let's look at 5. Initial velocity, final velocity, displacement, acceleration. Change in time isn't there, but acceleration is, so we can use this to solve for acceleration. So let's apply kinematic equation 5. So I'm going to write it over here really quick. I have final velocity squared equals initial velocity squared plus 2 times the acceleration times the displacement. All right, I can handle that. I'm looking for acceleration. So I could solve it like it is. I could plug it in and solve it like it is, or I could isolate the variable I'm looking for before I plug things in. And so that's what I'm going to do. I want to isolate acceleration. So I'm going to say my final velocity, I'm going to move this over, minus my initial velocity, all divided by 2 change in displacement, or 2 displacements, is equal to acceleration. All right, and now I just have to plug in my numbers. So I have acceleration is equal to my final velocity is 9.2 meters per second squared minus my initial velocity is 6.5 meters per second squared, all divided by 2 times my displacement, which is 48 meters. All right, I'm going to get my acceleration is equal to 0.4416 meters per second squared. My units came from my meters crossing out. One of my meters crossing out, so I'm left with 1 meter on the top in 2 seconds. All right, and Miss Neal just made a mistake when she solved this. I didn't set my positives and negatives before I started. So we're going to say that if this comes out positive, west is positive and east is negative. So it came out positive, so that helps me out. All right, so now I need to write my statement. So my statement is going to be the acceleration is, when I started, all of my numbers had 2.44 meters per second squared west. And there's my answer. All right, let's look at the next problem. Maybe it won't be so long, right? All right, example 2. After 5.2 seconds of uniform acceleration from rest, a spacecraft reaches an altitude of 5.7 times 10 squared meters up. What is the final velocity of the spacecraft? What is the acceleration of the spacecraft? All right, so let's draw a picture. I have a spacecraft. Oh, okay. Miss Neal has to draw a rocket ship. You don't want to see what the one in my notebook looks like. All right. And it starts at rest. So if this is my launch pad, I know my initial velocity is 0 meters per second. It's at rest. It's not going anywhere. And it reaches an altitude, so it gets all the way to the top. So here it is with its window. It's traveling up. And the problem tells us its final altitude is 5.7 times 10 squared meters up. And it wants to know what the final velocity of the spacecraft is. So for this one, it doesn't tell us what our displacement is, but we can assume that we're going to use our point of reference as the ground. So our initial displacement is going to be our initial position is the ground. So our displacement is going to be this final position, or this 5.7 times 10 squared meters up. So let's write out our kinematic variables, and then we're going to solve. So step 1 is to write out our kinematic variables. So our kinematic variables are displacement, initial velocity, final velocity, acceleration, and change in time. All right, we just said our displacement was 5.7 times 10 squared meters up. We know our initial velocity was 0 meters per second because the spacecraft started from rest. We're looking for our final velocity. We're looking for our acceleration. And we know our change in time is 5.2 seconds. So now we need to go to our kinematic equations. And the first one we're going to look for, we need to pick one variable to solve for first. And because final velocity is up here first, I'm going to choose final velocity. So I'm looking for an equation that has change in displacement, or displacement, change in position, initial velocity, final velocity, and change in time. All right, so number 1 has acceleration in it, and I need a problem that doesn't have acceleration. So we're going to solve for this one first and this one second. All right, so let's look at this one. It's looking good at the start. It doesn't have acceleration in it. Does it have displacement? Yes. Does it have initial velocity? You bet. Final velocity and change in time. So we're going to use equation 2. We're going to say that our displacement is equal to 1/2 times our final velocity minus our initial velocity times change in time. All right, and before I get started, I'm going to say that positive is up and negative is down. All right, so let's go ahead and isolate. We're solving for final velocity. So let's isolate final velocity. So I'm going to get 2 times displacement divided by change in time minus initial velocity equals my final velocity. All right, so now I'm going to plug in what I know. So my final velocity is what I'm solving for. I have 2 times, my displacement was 5.7 times 10 squared meters. My time was 5.2 seconds. My initial velocity was 0 meters per second. All right, so I'm going to get that my final velocity is equal to 219.23 meters per second, and I need a direction. And we said if it was positive, it was up. So my direction here is going to be up. All right, so now I can write this in up here. We know that this number we have solved, it's our final velocity is 219.23 meters per second up. All right, so that only answers the first question. We only found the final velocity of the spacecraft. We need to find the acceleration of the spacecraft. All right. We're going to use kinematic equation number 3. Kinematic equation number 3 already has that displacement nice and neat and pulled out to the front for us. So let's write that down. We're going to use, for the second half of the problem, kinematic equation 3, which says that our displacement is equal to our initial velocity times change in time plus 1/2 acceleration change in time squared. You can't see what I'm writing. All right. Now we just need to solve. And I'm going to make this, we're looking for acceleration. So we need to isolate this variable right here. We know our initial velocity is 0. So whenever we multiply times a 0, it gives us 0. So that's going to knock out this whole chunk. So now to make it a little easier to see, we're going to have our displacement is equal to 1/2 acceleration change in time squared. All right, we want to isolate acceleration. So we're going to get acceleration is equal to 2 times our displacement is equal to change in time squared. So my acceleration is equal to 2 times 5.7 times 10 squared up meters over our change in time was 5.2 seconds. When I solve, I'm going to get that my acceleration was 42.16 meters per second squared. We already said that positive was up. This is positive, so our direction here is up. So now I need to write a statement about what I solved for, and this is when I need to apply my sig figs. So my statement is going to be that the final velocity is, we look up at the top, everything has 2 sig figs. We need 2 sig figs, but right now we have 4. So we're going to round up 220 meters per second up, and the acceleration again, we need 2 sig figs, is 42 meters per second squared up. And there's our answer. All right, let's look at example 3. And I need a clean sheet of paper. I don't have one. We're just gonna have to use the back of one. All right, it says, what is the initial velocity of a car that reached 32 meters per second south in 3.4 seconds at a rate of 2.6 meters per second squared south? So we've got a car and it's driving. So I need to draw a car on a road. Road? Car. It looks like it's going to be driving backwards, but that's okay. What is the initial velocity? So when I go to write down here, I don't know what this initial velocity is. We know that it reached 32 meters per second south. Okay, so that's its final velocity. At a rate, or in 3.4 seconds. So our change in time is 3.4 seconds. And we know our rate, or our acceleration, was 2.6 meters per second squared south. So we're heading this way. So I'm going to set south as positive and north as negative. All right, so now I need to write down my variables. So I have my displacement variable, initial velocity, final velocity, acceleration, and change in time. All right. The problem doesn't say anything about displacement or location. It has velocity, time, acceleration, so we don't need displacement. I'm looking for my initial velocity, my final velocity is 32 meters per second south. My acceleration is 2.6 meters per second squared south. And my change in time is 3.4 seconds. All right. So we don't need change in displacement or change in position. So we need to find a problem that has change in time, acceleration, final velocity, and initial velocity. So if I look over here at my marks, equation 1 is the one that doesn't have displacement. So equation 1 is Sorry, I'm going to rearrange here for just a second so I can have something to write on. Well, that didn't work. I was going to put that underneath. Okay. Equation 1 is that my final velocity equals my initial velocity plus acceleration times change in time. And in this problem, I'm looking for initial velocity. So I'm going to rearrange to isolate initial velocity. So I get my initial velocity is equal to my final velocity minus acceleration change in time. All I have to do is plug it in. My final velocity is 32 meters per second. Minus my acceleration is 2.6 meters per second squared. My change in time was 3.4 seconds. So my initial velocity is equal to 23.16 meters per second. It's positive, so we know that direction is south. So now we need to give a statement and apply it to what it was looking for and apply our sig figs. So if we look at here at all of our givens, we have 2 sig figs and everything. So I am going to say the initial velocity is 23 meters per second south. All right, guys, we've got one more problem. Bear with me here. We're almost there. All right, so our problem says a cruise ship can accelerate at 0.01 meters per second squared. If it starts from rest, how long does it take to reach a speed of 25 kilometers per hour? So that's my first problem. And then it wants to know how long would it take if it started from a speed of 2 meters per second. So that's going to be a different variable. And we'll solve for that when we get here, or when we get there. The first thing we need to do is draw the knowns and unknowns, or draw a picture of what's going on. So we have a cruise ship. And my cruise ship is going to look more like a sailboat, because that's what I can draw. And we know that our cruise ship is accelerating at 0.01 meters per second squared. So my acceleration in my picture is 0.01 meters per second squared. And it wants to know if it starts from rest. So if this is where it starts, we know its initial velocity is 0 meters per second. We want to know how long it takes to reach a final velocity or a speed of 25 kilometers per hour. So this is a speed and not a velocity because we don't know direction. But we can assume, because we are dealing with a cruise ship and it's accelerating, that its direction is going to be forward. So I'm going to use forward as my direction. So I'm going to say if it's positive, it's going forward, and if it's negative, it's going backward. You could also drop velocity and change it to speed if you wanted to do that. So we're looking for how long it takes if it reaches a final velocity of 25 kilometers per hour. We're looking for change in time. We don't know what that might be. All right. So we are going to write down our kinematic variables. We have displacement, initial velocity, final velocity, acceleration, change in time. All right, we know it started from rest. We know it reached a speed of 25 kilometers per hour. We could figure out displacement if we wanted to, but it doesn't ask about displacement. It doesn't ask how far it went. It asks about how long. So I'm going to knock that out. We know our initial velocity is 0 meters per second. We know our final velocity is 25 kilometers per hour. We know our acceleration is 0.01 meters per second squared. And we're looking for our change in time. So we need a kinematic equation that doesn't have displacement. When we look at our chart, the one that doesn't have displacement marked is the first equation. So our first equation says that final velocity is equal to initial velocity plus acceleration change in time. And I'm looking for change in time, so I'm going to isolate change in time. So change in time is equal to final velocity minus initial velocity all over acceleration. And now I can plug my numbers in and solve. But before I plug my numbers in, I have a predicament. I have meters per second and meters per second, and then I have kilometers per hour. So that's not going to work. I'm going to need to change that kilometers per hour. And I'm going to need to change it to meters per second. So I have 25 kilometers in 1 hour. And every 1 kilometer, I have 1,000 meters. And every 3,600 seconds, I have 1 hour. My kilometers cancel, my hours cancel. I'm left with meters per second. My final velocity comes out to be 6.94 meters per second squared. Meters per second, not squared. All right. Now I can plug in what I know. My change in time is equal to 6.94 meters per second minus my initial velocity was 0 meters per second all over my acceleration, which is 0.01 meters per second squared. I'm going to solve and get that my change in time is equal to that looks like 694.4 seconds. That does me a whole lot of good. Do you know how many seconds 694.4 seconds is? Because I don't either. So let's convert that to units that are meaningful to us. So for every 60 seconds, we have 1 minute. Our seconds eliminate, and we get 11.57 minutes. That number makes a whole lot more sense. And it's positive, so we can say forward. All right. The second part of the problem wanted to know how long it would take if it started from a speed of 2 meters per second. So we're changing this initial velocity to 2 meters per second. We're still solving for a change in time. So we're going to do the exact same problem. We're going to say that our change in time is equal to our final velocity minus our initial velocity all over our acceleration, which means that our change in time is equal to 6.94 meters per second minus 2 meters per second, all over 0.01 meters per second squared. My change in time is going to be 494.4 seconds. Again, I don't know how long 494.4 seconds is, so I'm going to convert it into a unit of time that makes more sense to me. And I know for every 60 seconds, there's 1 minute. My seconds are going to cancel, and I'm going to get 8.24 minutes. All right, so my final step for every problem is to write a statement and apply significant figures. So I'm going to move my paper up. You won't be able to see the drawing anymore, but you will be able to see what I'm writing. I'm going to answer, therefore, if the ship begins from rest, it will take, I need to apply sig figs here. And I'm at 1. I need to get to 1 sig fig. So I'm going to say 10 minutes to reach 25 kilometers per hour. But if the ship begins from 2 meters per second, it will take 8 minutes to reach 25 kilometers per hour. All right, so those are our 4 problems for the day.